In this question, we will start by representing all the forces acting on this F1 car. So you can see that there's this upwards supporting force by the ground on the car, and this is the normal reaction force. Sometimes we call this the normal contact force by the ground. Alright, and there is definitely a forward engine force, FE. There is a downwards weight. There is a frictional force on the car, which is opposite in direction to the motion, which is backwards in this case, FR. And as the car moves faster and faster, there will be a significant air resistance. So that's FA, the force of air resistance. Okay, next we will need to use second law to do some calculations. So we are told that in part 1, the car accelerates at this value, very big value, 22 meters per second square, and we are to find the driving force, the engine force, the forward engine force needed to produce this humongous acceleration. So like all calculation question for forces, always define a direction, a vector direction that you want to be positive. So I always like to take the forward direction to be positive, and I will just write it down like this. And same technique for second law. On the right side, you plug in your mass, and the acceleration value is given to you also, 22 meters per second square. On the left side, you are to find the resultant force, which is literally summing up all the forces. So horizontally, there are 3 horizontal forces. There is a forward driving force, there is a backwards air resistant force, and there is a backwards frictional force. So we are given the value of the air resistant force and the frictional force. We must be very careful because these backward forces, we must represent it with a negative sign. So if you plug in the correct values, you will be able to get the driving force to be 21,600 newtons. Now in part 2, we are told that the velocity is constant. When the velocity is constant, what is the driving force? So whenever I see constant velocity, I always link it to acceleration being 0. And when this is the case, by Newton's second law, you will see that there are no resultant force on the object, and the forces must be balanced. This means to say that all the backward forces and all the forward force, this must be the same value. So immediately, my backward force is 1500 Newton and 2500 Newton. These two are the backward forces, which sums up to be 4000, and the driving force should take the same value. In part 3, we are told that the car now undergoes subsequent deceleration of 5 meters per second square. So the strategy to solve for part 3 is very similar to part 1. You are using Newton's second law, and on the right side, you must write down what is the acceleration value and what is the mass value. The acceleration value here takes a negative value because it's a deceleration. Deceleration means it's an acceleration in the backwards direction. Backwards is negative. So be very careful about the sign of this acceleration. Now on the left side, everything remains as usual. You are summing up all the forces acting on the car horizontally, and you have a driving force, and you have 2 backward forces, which must be represented using a negative sign. So when you solve for this, you realize that actually the driving force is 0 Newton. So this means that actually at that point in time, what the driver did was just to his legs is off the accelerator, and there is no driving force. The only forces acting on the car will be the backwards resistance and friction force, and this slows down the car as it moves forward with acceleration of negative 5 meters per second squared.